Topic for this video is solving inequalities in one variable, and the process for doing this will be very similar to what we did when we solved equations in one variable. You might notice there's a different symbol in here. All that symbol really indicates is that the values for the variable that will work in this equation are more than just one single value. When you solved equations with one variable, you found one value that would make this an equation true. In inequalities, there are several values for the variable that will make it true. Sometimes you will see symbols like just greater than or equal to, like I have in the problem. You may have less than or equal to, just less than, or just greater than. The process that you're going to use to solve these is no different than if you had an equal sign in the problem. You still need to undo any operations that there are in the inequality. And you undo them using the same methods that we did when we solved equations. So for example, in this inequality, we are adding 4 to x to find a value that's greater than or equal to 13. In order to undo the addition, we need to subtract. And again, we need to be certain that whatever we do to one side of the inequality, we do to the other side as well. So when I subtract 4 from 13, I'm left with 9. And my final statement says that x can have a value that is either greater than or equal to 9, which means numbers like 9 will make this sentence true, 10 will make that sentence true, 13 and a half will make the original inequality true. And again, if you're not sure of that, pick numbers that fit the description of this inequality. So if I pick a number that's greater than 9, I'm going to start with something easy. Let's just start with 10. 10 is greater than 9. Is 10 plus 4 giving me an answer that's greater than or equal to 13? That's my question. Well, 10 plus 4 is 14. 14 is certainly greater than 13, so yes, that works. If I were to choose a number that isn't in the description of this inequality, for example, let's choose 5. 5 is not greater than 9. 5 plus 4. Does that give me a number that's greater than or equal to 13? No, it gives me 9. 9 is not greater than or equal to 13. Well, the reason I'm getting a statement here that's not true is because I chose a number to plug in that was not part of the original solution set. The solution set, I needed to choose numbers that were greater than or equal to 9, and I decided to try a number that was less than 9, and you can see that it clearly does not work in that inequality. Okay, so let's try one where we have to do some other operations. For example, if I started with, an inequality that involved multiplication. So I have an inequality that says 2 times a number is less than or equal to 10. I want to find out what numbers can actually make that true. Well, in order to do that, I need to undo the operations that are affecting the variable. And right now that variable is being multiplied by 2. So to undo multiplication, I'm going to divide. Whatever I do to one side, I have to do to the other. 2 divided by 2 simplifies down to 1. So 1x is less than or equal to 10 divided by 2, which is 5. So this tells me that the numbers that will work in this original inequality are numbers that are less than 5 or equal to 5. For example, if I chose 0, is 2 times 0 going to give me an answer that's less than 10? That's the question. Well, 2 times 0 is 0. Is 0 less than or equal to 10? Yes, it is, certainly. Does 5 work in that original inequality? According to the solution set, it should. The solution set says that x is less than or equal to 5. So if I were to try 5 times 2, is that less than or equal to 10? 5 times 2 is 10. Is 10 less than or equal to 10? Well, it's not less than, but it is equal to. So yes, 5 does work, and our solution set does include any numbers that are less than or equal to 5. There is one time where finding solutions to inequalities is a little bit different than it is when we're solving equations. And I want to show you when that happens. And to do that, I'm going to start with a statement that I know is true, and hopefully you will agree with me. Sorry. That 3 is less than or equal to 7. 3 is a smaller number than 7. And let's say for some, I didn't include a variable in this on purpose because I just want to show you what happens when we perform a certain operation on both sides of an inequality. Let's say for some reason that we were told that we needed to multiply both sides of this inequality by -2. So I just put the parentheses there to show that I'm going to do multiplication. And when I multiply both sides by -2, I get a statement that says -6 is less than -14. Is -6 a smaller number than -14? Well, if you think of a number line, and we always put 0 in the middle, I'm sliding 0 over though a little bit because I want to be able to get numbers at least up to 14 on here. I'm probably going to go by 2's. So you have your -2 here, your -4 here, your -6, 8, 10, 12, and -14 actually goes way over here. On the number line, as you go farther to the right, the numbers get bigger. So in actuality, -6 is supposed to be bigger than -14. So when I multiplied both sides of the inequality by a negative number, it caused my inequality to become false. And in order to make it true, I have to change the direction of the symbol. Now, this is a true statement, and we want it to be a greater than symbol. And for our work with solving inequalities, what that means is anytime I multiply both sides of an inequality by a negative number, in order to maintain a true statement or find solutions that actually do work, I'm going to have to change the direction of the symbol. And because multiplication and division are inverse operations of each other, not only will we have to make that change when we multiply but we'll also have to make that change when we divide. So for example, let's put something in here where we're actually solving an inequality. My inequality says that when I take x and multiply it by a negative number, I want to get answers that are less than 15. So we're going to go through and solve this. We're going to divide both sides by -3 because division is what undoes multiplication. And these -3's now reduce to 1's, so we just have an x over here. And let's say we didn't think to change the direction of the symbol, and we ended up with an answer that says x is less than -5. What that's telling me is my solutions to this problem are numbers that are less than -5. Let's try some. Something smaller than -5 that's easy to work with would be a -10. So let's see, -3 times -10. Does that give me a number that's smaller than, smaller than 15? Well, -3 times -10 is 30. Is 30 smaller than 15? No, it's not. 30 is much bigger than 15. I'd rather have $30 in my pocket than $15 in my pocket. So because I failed to change the direction of this symbol when I divided by a negative, I got incorrect solutions. Let's see what happens when I change it to being greater than -5. So now a number that's greater than -5 and easy to work with is, I like to use 0 if I can. So -3 times 0, does that give me an answer less than 15? Well, -3 times 0 is 0. Is 0 less than 15? Yes, it is. I'd rather have 15 in my pocket, so 0's got to be smaller. So my solution, x is greater than -5, does work.